Yes, we do.
Yeah, so I can start, right?
Yes, please go ahead.
Yeah, hello everybody. Thank you for coming here and joining me. I will try to finish as quick as possible. So this is my research. This is our research, which is reflective crack mitigation using thin layer of ECC as an interlayer system. So here is the, there are 4 authors I am presenting in lieu of them. I was closely associated with the research. So I am Mohammad Reza Bhuyan, a graduate student from the university. So here is the outline. We have background and motivation, experimental program, result and discussion, and then conclusion. So here you are watching a composite pavement where the base is PCC, cement concrete, and then there are joints in the composite pavement, and that joint you have a reflective crack over the from that joint to overlay. So in the composite pavement, there are PCC base. Over the PCC base, there is a asphalt HMA layer. That HMA layer will have a reflective crack over time at the joints. So how to stop or mitigate that reflective crack, that's our objective of this research. So there are various treatments existing, which is interlayer, saw and seal, crack and seal, geosynthetics, geotextile, to stop this reflective crack. But there is no adequate solution up until now. So we are trying to solve the problem by a new interlayer. So that interlayer is ECC, engineered cementitious concrete, which is a kind of concrete, but it has no coarse aggregate. It has river sand, and it has polyvinyl alcohol fiber in it. And you see the 4-point bending test. It is very ductile. It has strain hardening behavior with high tensile ductility. It has large deflection capacity, so it can deflect more. So if you see the stress versus strain diagram at the bottom, at the back, you will see the traditional concrete is failing here at 0.3% strain, and ECC is going up to until 5%. So it can take a lot. It can take a lot of strain before it fails. So that's make it a potential candidate for a good interlayer for composite pavements reflective crack. So we did some experiment by laboratory experiment we try to see, we would like to see that how ECC work as an interlayer. So ECC, here is the ingredients of ECC: cement, fly ash, river sand, water admixture, and polyvinyl alcohol fiber. You see the fiber at the right. So it's 10. It's a 1 centimeter fiber, 10 mm, and we mix this and make the ECC beam, which is a 1/2 inch beam. And we placed HMA 2-inch overlay, HMA mix, and underneath we had a PCC base, and that's our sample. You see, this is the interlayer sample, where you have, this is the PCC base, and over the PCC base we have the ECC interlayer, which is 1/2 inch, 12.5 mm, and PCC base is 2-inch, 50 mm, and over it we have a HMA beam. And then we applied a distributed load, and underneath the entire system there is a neoprene rubber, which is giving a continuous support. So we are giving fatigue load to this sample, and we are comparing with control sample without any interlayer. So we have control sample where there is no interlayer with this test setup, and we have interlayer sample with this image, and we have fatigue life for both, and we are comparing them both. So for interlayer, we have 3 kinds of sample. One is fully bonded, another is half bonded, another is pre-cracked sample. So fully bonded means, you see the ECC beam and concrete base, there is the epoxy glue. Fully bonded means it's entirely 12-inch, throughout ECC epoxy glue. This is fully bonded. Half bonded mean at the middle portion, 6-inch, there is no bonding between ECC and PCC. And pre-cracked sample means we break the ECC beam in material testing system by a 4-point bending load with 15 mm deflection, and then we place that ECC beam and use it as an interlayer. So to see that in extreme condition when our ECC beam is already broken, does it really work after it is broken? So to do that, we checked, we did the same experiment on pre-cracked samples where ECC beam is cracked. So here is some images. You can see the testing for HMA and PCC, and at the back side we have LVDT at top and bottom of the HMA, and we are applying Haversine load. We are giving 95 psi of load at the peak. So we have placed this distributed load over it, this fatigue load, and until the sample fail, we run the test. And we are also taking the images of the sample by digital image correlation technique, and we are analyzing the strain behavior by the imaging. So we are calculating the fatigue life of the sample from the LVDT data and extensometer data, which is at the back. And we are calculating it from the normalized compliance. So you know, compliance is reverse of elasticity. So when the elasticity became half, compliance became doubled. When the compliance is doubled, we consider the sample as failed. And we see some cracking coming up in the sample also. So we are calculating fatigue life with the criteria that when the compliance is double or elasticity of the matter is half, then the sample is failed. Failed means it initiates crack, and that's the fatigue life. And we are confirming it from DIC observation, and we are comparing control sample versus interlayer sample. And we are watching whether interlayer, is it working? It is increasing the life or not. So here is some example. So you are watching two different graphs. At the left, you see the elastic strain graph. And if you divide the time series elastic strain by the first value, initial value, you get the normal compliance. So when the normal compliance is 2, the sample has initiated crack and it is failed. So that's how we are doing it. And we see that average fatigue life, I mean the crack initiation, is 1930 or 2000 cycles for control sample. And for half bonded sample, it's 92,000, so almost 40 times. Fully bonded sample is 58,000 cycles, almost 30 times more. So ECC gives a real improvement in fatigue life for half bonded and fully bonded sample. Interestingly, half bonded sample gives more life than fully bonded sample. So that's one of the results, and you can see the image. The control sample, you see at 3000 cycle, and at 5000 cycle the cracking is there. So at 2000 it shows failure, but full depth crack came up at 5 to 6000. And this is von Mises strain. You see the red color is higher strain and the green color is lower strain, but it's tensile. It's mostly tensile strain at x-axis. So if you see the strain, the control has 4.46% strain. The half bonded developed 5.45% strain, and the strain is distributed to a wider area, which explains why it is delaying the crack. So if you see the fully bonded interlayer sample, the entire area has higher strain, and life is increased. And for control sample, there is a one single point where is highest strain and it failed. So it explains that how ECC is delaying the crack initiation and increasing the fatigue life for both samples. So we have similar type of failure at 80,000 cycle and 84,000 cycle for half bonded and fully bonded, when it is in control at 55,000 only. So ECC is really working good. And for full depth crack penetration, 5,000 for control sample, 120,000 for half bonded sample, and 96,000 for fully bonded sample. That's the time. That's the number of cycles we need for a full depth crack penetration. So ECC is really working and it's increasing the life. So this is for pre-cracked sample. So I told you before that we have pre-cracked sample. So we pre-crack the ECC and we see the 10, 11 micro crack is there. It's watchable in naked eye. We can see it. So it's kind of very broken ECC, and we placed this ECC here. So this sample also were able to significantly delay the crack propagation It's still a reflective crack, but see 2000 cycle control sample failed, and this sample failed at 11,000 cycle. And the image is showing 17,000 though. So still there is an improvement, 3-4 time improvement. It means in the field, if we place ECC and ECC is already broken because of any reason, it will work. It will not make problem. It will at that time probably work. So that's the results. And you see the number of cycle versus different type of samples. You see control sample is failing at very low cycle, 2000, 5000. Half bonded ECC, fully bonded ECC, pre-cracked ECC, all are giving significant life improvement. So to conclude, I would say ECC interlayer, it successfully arrests reflective crack, resulting in a dramatic increase of fatigue life for 30 to 40 times. Fully bonded and half bonded ECC, they both did good, and it gives significant increase of fatigue life, and it distributed the strain, which can correlate to stress. It distributed the strain to a wider area, and it create multiple cracks here and there, and that's the reason why it delays the fatigue life, and it was able to have a life 21 times at least. And when the ECC sample is severely cracked, still it gives 5 to 6 times extra life, fatigue life, with respect to control samples. So ECC, we hope that it will work, and we probably can try it for ALF testing or other testing, and we hope it will work as a good interlayer for composite pavements. So here is my research. Thank you all. Is there any question?
Great, thank you very much. We have time for one question, maybe, if anyone has one.
I have a question here. My name is Mina Solomon. I'm an associate professor at the University of Texas at Tyler. Good presentation, and I like the concept. I was just wondering if you had the chance to do any cost to benefit ratio. We got to see that it has 20 or 40 times the fatigue life, which is great. And I think if I were to do the same testing, I wouldn't be surprised to get that benefit. But how much, what's the cost associated with it? And I still think you can justify the added cost, but I think it would be nice to show this in future enhancement of this research.
Thank you for the question. It's a concern. We know it. We did not did any evaluation for cost effectiveness, but ECC is actually costly. It has PVC fiber in it, so it is costly. And how to implement it in the field, is it precast or postcast, depends. So we will do it in future. We have a plan, but currently we don't have it. We can do it future. Okay, thank you.
Great, thank you very much. And I know we have further in the program, in some future sessions, some more presentations on ECC. So if that is a subject you're interested in, take a look in the program to see about some future presentations. So with that, I am going to conclude this session 1B on pavements. We do have our next set of sessions starting at 10:30, so I want to give everyone time to transition. We have session 2A, which is a structural session, and session 2B, which is a geotechnical session. So thank you all for coming. I saw at the peak we had 73 attendees in this session. So thank you all for your interest and participation today. And I look forward to seeing you in future sessions. So with that, I am going to end this session. Thank you.
Thank you.